Now I should have sound. That is way too loud. Well, half the presentation will have sound. So, the scanning spectrophotometer uses... Now I should have sound. That was my phone reminding me I had sound. So the scanning spectrophotometer provides an instrument that links the theory from these rudimentary stripped instruments to an industrial instrument. It uses an Arduino-based circuit to scan through the spectrum and take measurements before calculating absorbance. So this Arduino is an open-sourced microcontroller. It's a microchip that, among other things, that is able to control whatever I program it to do. And so using this, an RGB LED, a photodetector, and an LCD screen, I was able to program the Arduino to tell the LED to cycle through the different wavelengths of light from red to purple to violet, go through a sample, and then detect it using a voltage divider circuit, and then automatically calculate the absorbance values. Very similar to an industrial instrument, or the microlab systems, or the small vernier UV-vis spectrometers that we use on campus. And the purpose of this was twofold. One, to provide low-cost instrumentation to schools and to levels that may not be able to afford it, as this entire design is less than $100. I should note, that's the point of most of this presentation. All of these are low cost, they're full 3D printed, so there's an upfront cost of the 3D printer and material, but each instrument itself is, for the 2021 design, less than $50. This Arduino base is less than $100. And so using this Arduino based circuit, students would be able to see how the instrument actually measures the different wavelengths of light and the absorbance. And it makes it so that we can not worry about taking the lid off the $100 instrument and possibly spilling on it and ruining it, whereas the $40,000 instrument in OT, we wouldn't necessarily want to take a full Gen Chem class into for fear of possibly spilling. So, like I mentioned with the projection-based spectrometer, this was the main instrument we are currently pursuing. So we implemented this instrument alongside of our 2021 design into the general chemistry course in this semester, fall 2022. The lab was at the beginning of the year. It was their third lab, and they used their 2021 design to take quantitative measurements like they did last year. However, before putting their sample into the quantitative instrument, they would put it into the projection-based instrument, and they would observe what wavelengths of light were absorbed. And I have some actual images of some of the things they did here in a moment. Alongside this, we implemented pre and post demographic surveys, as well as diagnostic assessments to gauge student understanding, to gauge where they were at before, where they were at after, how much they learned from the lab, their opinions on the lab as well, through some qualitative questioning, as well as these demographic surveys. So what did this actually look like? So this is the block diagram I showed you earlier. A reminder to look at the green disappearing. This is what the instrument actually looks like and what the spectra actually looks like. I have the instrument here in the back that I can show you later if you would like. But if we look at this picture on the left, you have the white beam path going straight through, and then you have the visible spectrum on the right. On the right picture, this is using a red food coloring sample, I believe. And so in the center, you see the full transmitted light is red. If I shine a light through red Kool-Aid, it's going to be red on the other side. So that is 100% transmittance through the red sample. And then on the right, after the diffraction grading, you have the full spectra. And if we look, oh, I didn't put arrows in. So if you look at the green area, obviously that would be right after the blue. You can see on the left that it's very bright, whereas on the right, there's just kind of a dark spot. There isn't much color there. You can kind of see it. That is the same absorbance that I was referring to earlier. So with a red sample, green would be absorbed. So after putting their sample into the projection instrument, They would then move on to calculations and quantitative measurements. So just to remind you of the three different equations they're using, transmittance is equal to the voltage of the sample over the voltage of the blank. Absorbance is equal to the negative log of transmittance, and then the absorbance is equal to the molar absorptivity constant times length times concentration. So this is what their data ended up looking like. This is an example, and I made it so that you may be able to actually see where certain equations took place. I should note that here the transmittance looks a little bit different. This is the full transmittance equation that accounts for the limit of detection of your instrument. We took that out because it was essentially 0, and many students, it became an obstacle for students from understanding the goal of what we wanted them to see. So moving from left to right, you have the wavelength of light, the color of your light, the dark voltage, which again, we're just kind of ignore for now. That is the limit of detection. And you have your blank, and you have the voltage of copper chloride, which is the sample. This, you would divide your copper chloride by your blank to find your transmittance, and then you can find your absorbance off of that. But now what's the point of calculating this absorbance? Well, using that, we can create a spectral absorbance graph. And this one, I put a rainbow across the background so that you could see about where the colors were. So moving from left to right, we have violet to red, and this line represents where the sample is absorbing color. So the blue line is going to be copper chloride, which is a blue sample, and you notice that it spikes at orange and red. A blue sample would absorb orange and red samples. Whereas the cobalt chloride is a red sample, so it would absorb around the green wavelengths of light. And then after finding this, students would decide on a color and a sample to use. So if they chose cobalt chloride, they would use a green LED, and they could make a graph of different concentrations and figure out an unknown concentration using that Beer-Lambert's equation. So what did we see after doing this? Like I said, we used diagnostic assessments, we used pre and post demographic surveys, we used qualitative analysis to try and tease out as much information of the student learning outcomes as we could. And so for the results, we saw that the average score per question on the pre and post diagnostic assessments were statistically different. Using a population sample of 52 students and a confidence alpha of 0.05. Again, a lot of words. Basically, we saw that the pre and post exam scores were different statistically, meaning that we can say that student understanding did improve. As you can see, the post-lab assessment had an average of 54% per question. And that seems really low, but keep in mind that I graded based on a 0 to 2 basis. So 0 was incorrect, 1 was partially correct, 2 was fully correct. So there isn't a lot of range there to get full credit or partial credit. There's not a whole lot of range to get a multitude of percentages. I do want to draw your eye to question 2 on this chart. This chart on the darker blue is the pre-test average score, and the light blue is a post-test average score. Question 2 asked about the relationship of the color of the solution and the color of light absorbed. As I've said many times throughout this lecture, the complementary color is what is absorbed to maybe be able to see an even larger jump. But there are many conflicting variables with this. Between a pre and post test, you just see that students learn from the lab. You don't truly see that they understood all your objectives, that the objectives they understood were because of this specific instrument. You know that they understood your objectives based on the lab overall. So we had to use other methods to try and discern and tease out the effect of the implementation of this projection-based design. So using survey analysis, as well as some specific targeted student questioning, we attempted to tease out some of these more fine details of the lab. So this is from our qualitative demographic survey. These questions were specifically relating to the 3D printed instruments. from the instrument usability. How easy was it used? Did it improve your understanding? Did the instruments connect to one another? Did the qualitative instrument help you understand what was happening inside of the quantitative instrument, the 2021 design? How well did the 3D printed instruments help you understand the lecture content? If this instrument doesn't help us understand the underlying theory, then it isn't helping us understand the full extent of the chemistry that's occurring. And then finally, how well did students enjoy using the instruments? It's fun to use something new in class, something novel. So did students enjoy using it? Did it increase their student self-efficacy in class and in lab? And overall, this was on a 1 to 5 point scale, 1 being strongly disagree to statements, and 5 being strongly agree to the statements that we asked. And we saw an overall agree. These instruments were easy to use. The instruments were fun to use. The instruments helped me understand the underlying theory better. Now, we did cherry pick this quote, but it's a good quote, so I'm going to give it to you. The projection spectrometer was most helpful because it gave me a visual representation that I could apply to my understanding of light properties. We saw this occurrence a few times throughout the comment section that we offered with targeted student questioning. However, there are still shortcomings, still things that we want to try and improve, still things that we want to try and tease out. How can we better improve this lab? How can we help students better understand the underlying content? So although students walked away with many of the learning outcomes, there were still things missing. So the first thing that I saw when grading was that many students called light color. So back to the qualitative instrument, you saw the full spectrum of color and the color absorbed. But that's how students were phrasing it. They were talking about the color absorbed, rather than saying that it is the color of light absorbed. And although it is a small vocabulary and grammatical difference, it is crucial to understanding what is occurring at the atomic and electronic level, to understand that it is light doing the work and not just the colors I chose in my art class. It's crucial to understand that difference. And then we also saw that there were some missed connections of lecture content to laboratory material, similar to what I said. Because they saw colors and not just the color of light, students missed that it was the electrons doing the absorbing, which is crucial to understanding how electrons function. So future direction, and I'm moving really fast. Future direction with this project. So for the projection instrument, currently we are going through the documentation, we are going through the grading, going through all the data we've collected to try and draw more conclusions. And we are moving towards compiling our methodology and results into a cohesive article towards publication in an academic journal, looking to offer this information to the academic community so that other people can implement this, other people can see the good that this has done for our school and possibly implement it, or see if they can implement it in a different way at their own school to better student understanding at the instrumental curriculum. We wish to address these missed learning outcomes to better our own curriculum, better the general chemistry laboratory experience, so that students would be able to see these learning outcomes better. And we want to review the documentation to allow all students to reach the same level of understanding. What we saw in Gen Chem, and I didn't put it in here because it isn't a firm conclusion, but we saw a loose relationship or correlation between the students that understood and were able to connect the instruments to the lecture content of electrons were the chemistry majors, were the higher achieving academic students. So how can we take this content and adapt it so that all students of all achievement, of all majors taking general chemistry can understand the same lecture content can reach the same level of understanding of the electron and atomic level that is occurring within the instrument. For the modular instrument, we are looking to refine the instrument. Currently, if you put the instrument together and try and take a measurement, it falls over if you aren't using F-clamps on it. So looking at a way to refine this instrument to make it more usable, more able to be implemented into the curriculum. And then we plan to implement this into analytical chemistry in the 2023-2024 school year, measuring effect on student understanding. We're looking at our upper level 300s level course as it is more of upper level ideas and concepts, seeing the connection and lines drawn between various instruments and between new theories. And finally, the scanning instrument, we are doing further research into prior work to understand what has already been done, to see if we can further the work, see if we can find something new to do with that, or if the best course of action is just to implement the prior research into curriculum to help scaffold the entirety of a student's learning of instrumentation. Man, I move really fast. So for acknowledgements, I want to acknowledge Andrew Wantz. He worked on the 2021 design that we implemented. He did prior work into 3D CAD softwares, into 3D printers, so that I didn't have to search for a printer and a software to use. I was already prepared to do my work. Thank you to the Hodson Research Institute for funding this research, to Dr. Stephen Tripp for the opportunity, experience, idea, and supervision of the project. And then Dr. Jeff Tabone for helping with reservation and logistics for this presentation. And then finally, thank you to my loved ones for listening to my unending ideas and incessant rambling about the research, whether you understood it or not. If you want to know more about the references, I can show them later. Thank you, and if you have any questions, I'll be around. I can do them now in front of people, or if you have them, or you can come up and ask me individually. I didn't plan this far ahead.
I have a question.
Yeah.
I am not a chemistry major, and I remember having a hard time in chemistry lab. But I had a question about, you were saying it absorbs the light.
Yes.
So I'm correct in saying light, not
Yes.
color. But you still see some of the green there? Like
Yes.
You said, so I was just curious about that. Is that like a common
So-
or is that just molecular level?
So, on one of the slides, there we go. So there you can still see some of the green. That actually has to do with this last equation, the Beer-Lambert's law. A equals some constant, the path length, and then concentration. So if I have red Kool-Aid and I shine light through it, there's still light getting through. Whereas the more and more Kool-Aid I add, the less light will get through. The more red it will be, the more green that's absorbed. So it depends on the concentration of your sample. If it's super concentrated, less and less light will get absorbed. It also depends on this molar absorptivity constant, which has to do with how well it interacts with the light, how many interactions that actually occur when you shine light through. As well as, in science, we have something called quality analysis and quality control. How precise do you need to be? How, at the general chemistry level, we aren't looking for 100% concentration, 100% absorbance. As well as to get to 100% absorbance, basically just have to put something in the way. But, yeah.
Cool. Very helpful.
Yeah. Yeah.
Brandon, I can think of distinctive moments that cause me to fall in love with their style. What is it about spectrometers? What is it about this experience that obviously has captivated you in ways that maybe the rest of us are not as familiar?
Yeah. So for me, it's not necessarily the spectrophotometers that I fell in love with. It is the idea of low cost, which looking back I kind of skimmed over in the presentation. As I said, the instruments are extremely low cost. The 2021 design is $50. The Arduino base is $100, whereas the little boxes we use that only do spectrophotometry are, I believe, $600, $600. The microlab units we implement that can do multiple experiments are $1,500, I think. $1,200, $1,500, something like that. With them being low cost, you can implement them into low-cost colleges. You can bring them down to high school level classrooms that don't have the same budget that collegiate level colleges have. As well as the 3D printing aspect is just something that you can apply to a multitude of different experiences and different lab techniques, different models. For another class, I wrote a research proposal of just implementing 3D printed models into the high school curriculum. I believe collegiate level has, I want to say the college I looked at had a budget of $200 million, whereas the high school I looked at had just under $1 million. So that discrepancy makes it so that you have to be a little bit smarter and more creative about what you use at the high school level and in low income. And 3D printing allows you to create creative, useful, and individual models that you can pass around to students, not worry about them getting broken. There's an upfront cost of about $1,000 for the printer, for materials, but once you do that, the instruments themselves are extremely inexpensive. The actual instrument, the 2021 design, the plastic used I think was about $7 worth of plastic. No, the projection was $7. The 2021 design was about $13 worth of plastic. So just the cost effectiveness makes it so that these models and these instruments can be used at any level. And I plan on using them in my own classroom, so. Any other questions? Yeah. Not yet. We haven't made any connections yet. One thing we are looking to do, the general chemistry labs are taught by different professors. So one of the things we're going to look at is how does the professor that's teaching it relate to how many students understood the connection to lecture content. Is it something that one specific professor is doing? Is it that we need to implement some other model or some other content into the lab to help students see that connection? So we haven't drawn all those conclusions to see what helps students do that, but we are looking to see what has done that so far. Yeah.
Are your chemistry labs taught prior to or following a lecture on the same material? The Beer's Law lecture, is that done before a lab or after a lab?
So there is not a Beer's Law lecture as far as I remember. It is built into the lab. So that students are supposed to do a reading over absorbance, transmittance, and Beer's Law themselves, go through the appendix of the lab manual and read through it themselves to understand it. How many students do it? I mean, I know I didn't. But students are supposed to expose themselves through reading to that. They have had a lecture over electron configurations with the new textbook that they're using this year, last year.
And has there been any thought to taking the lecture lab and instead of doing the traditional 1 hour, 3 days a week for a lecture, and a 3-hour lab sometime during the week, breaking up into 2-hour blocks where you do the lab lecture on top of one?
Maybe. I don't get paid to make those decisions. I won't say that it is out of the question, but that is something that is up to the faculty.
Just in the work here that I'm concerned with the same thing, so I'm just curious how
Yeah.
academia was doing it, because we've tried to pattern training in the real world environment after a lot of academia to try and keep those same levels of education for people we have to train.
Yeah. Yeah.
Just because I'm colorblind, I can't see the read the picture that you showed.
Probably.
We'll stick your head in this bucket.
They have those colorblind glasses. Those could be helpful. The other thing is the picture I showed of the projection spectrophotometer is an older one. I have refined it a little bit with narrower slit widths, which makes it so that there's less blurriness. You can see clearer the difference between the colors. So it is easier to see. One other thing that we have thought about is trying to make the projection spectrophotometer quantitative by using a photodiode array or a charge coupled device array. And basically by doing that, you can see the projection, but then you could slide a detector that would measure all the wavelengths at once. So those people that were colorblind could look at the numbers to say, oh yeah, there's less light there. Would be another option. Any other questions? Well, thank you guys very much for coming out.